Returning to the task at hand, engineering prefixes concern themselves solely with powers of 10 in three-step shifts. Positive powers of 10, like 10 raised to the third, 10 raised to the sixth, 10 raised to the ninth, and so on, are associated with leftward shifts associated with ever greater larger numbers, whereas negative powers of 10, like 10 to the negative third, 10 to the negative sixth, and 10 to the negative ninth, and so on, are associated with rightward shifts associated with ever smaller small numbers. Consider the expression 10 raised to the negative third. This means take 1 over 10 and raise 10 to the third power. 10 to the third power is 1,000. 1 over 1,000, or 1,000th in decimal form, is 0.001. Similarly, consider the expression 10 to the negative 6. This means take 1 over 10 and raise 10 to the sixth power, where 10 to the sixth is a million. 1 over a million, or 1 millionth in decimal format, is 0.000001. Consider the expression 10 raised to the negative ninth. This means take 1 over 10 and raise 10 to the ninth power. 10 to the ninth is a billion. 1 over a billion, or 1 billionth in decimal format, is 0.000000001. Lastly, consider the expression 10 raised to the negative 12th. This means take 1 over 10 and raise 10 to the 12th power, where 10 to the 12th is a trillion. 1 over a trillion, or 1 trillionth in decimal format, is 0.00000000001. You'll ultimately realize these negative powers of 10 are in effect multipliers that make a given coefficient smaller and can be used to express extremely small numbers in a compact, usable fashion. Quite like positive powers of 10, negative powers of 10 also have their own associated engineering prefixes. Numbers multiplied by thousandth, or 0.001, get a milli prefix, which is written as a small m. Numbers multiplied by millionth, or 0.000001, get a micro prefix, which is written as a funny-looking U with a long tail. Lacking the proper key for this symbol, or more appropriately, lacking the will and motivation to look up the proper shortcut for this strange symbol, you often see micro written as a regular lowercase u. Continuing in this fashion, numbers multiplied by a billionth, or 0.000000001, get a nano prefix, which is written as a small n. And lastly, numbers multiplied by a trillionth, or 0.00000000001, get a pico prefix, which is written as a small p. Let's combine this new set of prefixes associated with small numbers with their earlier set associated with large numbers. And now present to you the set of the most commonly used engineering prefixes covering the spectrum from the unimaginably large to the inconceivably small, a trillion to a trillionth, 10 to the 12th, tera, or big T, 10 to the 9th, giga, or big G, 10 to the 6th, mega, or big M, 10 to the 3rd, kilo, or lowercase k, the base unit necessitating no prefix. Now it's mirror image, 10 to the negative 3, milli, or lowercase m, 10 to the negative 6, micro, or u with a funny tail, 10 to the negative 9th, nano, or lowercase n, and finally 10 to the negative 12th, pico, or lowercase p. Chances are you'll never have the occasion to use anything above or below the ranges I've presented here. My sincere advice is to take the time necessary to commit this relationship to memory. I say again, my sincere advice is to take the time necessary to commit this relationship to memory. Because one day, someone's going to take it away. Ha, just kidding. I bet you freaked out there. Don't worry, I'll just keep this cheat sheet on the screen for a little bit so you can copy it down in your notebook. Similar to the advice I issued earlier about the upper range of engineering prefixes, I've found a far simpler way of thinking about engineering notation at the smaller end, or for that matter either end, is to simply move the decimal point left or right in three-step increments as required. Each engineering prefix gets 3 spaces. When expressing a number in the base unit, the decimal place is here. The next larger prefix to the left is kilo. The next larger prefix to the left is mega. The next larger prefix to the left is giga. The next larger prefix to the left is tera. Our last set of example problems dealt with these larger numbers. Smaller numbers are similar, only they're on the right. Starting at the base unit, the decimal place is here. The next smaller prefix to the right is milli. The next smaller prefix to the right is micro. The next smaller prefix to the right is nano. The next smaller prefix to the right is pico. Every prefix gets 3 spaces. As previously, if you think in this fashion, one can lay out any number of interest in a horizontal row and just see which vertical prefix common is the most appropriate. For example, consider the number 0.00002 amps. I know you don't normally see them in smaller numbers, but where would you put a comma in such a long string of numbers? Chances are right here. Again, think in groups of 3. You know, at the very far right side isn't a group of 3, but rather only 2. Feel free to add another 0 to make it a group of 3 because there's an endless string of invisible zeros behind every number, and you can add or not add as many as you like. Our number of interest is now 0.000020 divided into 2 groups of 3. As previously, if we overlay the number on the vertical columns associated with each engineering prefix, we see it's inside the micro range. If we move the decimal place right 6 spaces, or negative 6 spaces if you will, it gives us a coefficient of 20, i.e. something 1 or greater and less than 1,000. A 6 decimal point jump right is a micro, so this number might be more compactly expressed as 20 microamps. An amp, by the way, is a unit of current flow, i.e. a quantity of charges passing by a point in space per unit time. We'll examine current and other electrical properties in later lectures. Similarly, consider the extremely small number 0.00000000033 farads, where a farad is a quantity of charges stored per volt associated with a type of electrical component called a capacitor. We'll examine capacitors in later lectures. Can we use engineering prefixes to tame this wild herd of zeros and represent this unwieldy measurement in a more docile and manageable form? Yes we can. Allow me to demonstrate. Break this tangled mass of zeros into 4 groups of 3s. Overlay the vertical columns associated with each engineering prefix and see where it most comfortably resides. We see it's inside the pico range. If we move the decimal point right 12 spaces, or negative 12 spaces if you will, it gives us a coefficient of 33, i.e. something 1 or greater and less than 1,000. A 12 decimal point jump right is a pico, so this number might be more compactly expressed as 33 picofarads. Want to give this a go yourself? Be my guest. Here's a couple of extremely small numbers. See if you can use your new understanding of engineering prefixes to put them in the proper engineering format. Again, don't worry so much about what each unit represents right now. We'll examine the units and quantities they represent in later lectures. By all means, pause the lecture and try these examples by yourself. If you're tracking, you should obtain the following values. Our first entry, 0.120 henries, is better expressed as 120 millihenries. Our next entry, 0.0000022 coulombs, is more appropriately represented as 2.2 microcoulombs. Our next entry, 0.03 amps, is better represented as 30 milliamps. And lastly, 0.000000015 farads is more compactly represented as 15 nanofarads. Alright, if this last part went well, you're most likely now getting a tentative hold on placing small numbers in proper engineering format. Let's finish up this lecture with a set of illustrated examples featuring both small and large numbers. If you can survive this meeting engagement with your sense of dignity intact, you're tracking and you can move on to the next lecture. If not, you are not tracking and you need to rewind or revisit the contents of this lecture. As I mentioned previously, engineers and technicians use engineering prefixes, and if you can't use engineering prefixes, you can't be an engineer or technician. Learn this technique now and put it behind you quick, because I got a bunch of other stuff coming your way real soon. Alright, see if you can place these unwieldy numbers in proper engineering format, where proper engineering format again uses a coefficient 1 or greater and less than 1,000, and a prefix representing a magnitude. Feel free to use the prefixes overlay if that helps you out. By all means, pause the lecture and try these examples by yourself. If you're tracking, you should have obtained the following values. For our first example, 4,200,000 hertz is more appropriately expressed as 4.2 megahertz. Our next entry, 0.0345 amps, is more appropriately represented as 34.5 milliamps. Our next example, 0.00004 farads, is more appropriately represented as 40 microfarads. Our next example, 12 volts, is already in proper engineering format, so 12 volts is most appropriately expressed as 12 volts. Our next example, 10 billion watts, is best expressed as 10 gigawatts. Our next example, 5,700 watt-hours, is more appropriately expressed as 5.7 kilowatt-hours. Our next entry, 0.00000000630 farads, is more compactly represented as 630 picofarads. Our next entry, 34 trillion joules, is more appropriately represented as 34 terajoules. Lastly, 0.000000001 meters is more appropriately represented as 1 nanometer. All right, if that last part went well, I hereby proclaim you marginally proficient in engineering prefixes. If I was a lesser instructor, unconcerned about your future, we'd probably call it quits and let you go outside to play. But that's not why you're here, is it? You're here for my own special brand of cold, hard discipline. Am I right? Let's try one more exercise before we bring this lecture to a close. Consider the selection of entries, each a measurement of the fictitious unit of surprise specified in the units of zoinks, abbreviated with a capital Z, where surprise of 1 megazoink is sufficient to stampede a herd of water buffalo, whereas a surprise of only 1 millizoink is barely enough surprise to register notice, like, say, seeing a water buffalo next to a body of water. I'm asking you to do 2 tasks. 1, place these entries in proper engineering format, and 2, arrange them in a sequence largest to smallest. Again, I'm asking you to do 2 tasks. 1, place these entries in proper engineering format, and 2, arrange them in sequence largest to smallest. By all means, pause the lecture and try this yourself. If you're tracking, you should have obtained the following values. Our first entry, 33,000 zoinks, is better expressed as 33 kilozoinks. Our next entry, 23,800,000 zoinks, is better expressed as 23.8 megazoinks. Our next entry, 24 zoinks, is already in proper engineering format, so 24 zoinks in proper engineering format is 24 zoinks. Our next entry, 0.196 zoinks, is more compactly expressed as 196 millizoinks. Our next entry, 8,700,000,000 zoinks, is more usably expressed as 8.7 gigazoinks. Our next entry, 0.047 zoinks, is more appropriately expressed as 47 millizoinks. Something 1,000 times smaller, or 0.000047 zoinks, is more appropriately expressed as 47 microzoinks. This large value of 2,840,000,000,000 zoinks is better expressed as 2.84 terazoinks. And lastly, this extremely small value of 0.0000000000022 zoinks is more efficiently expressed as 22 picozoinks. Lastly, we've been asked to arrange these entries in a sequence. This is where engineering prefixes truly show their worth. For a quick discernment of magnitude, one can simply ignore the coefficient and look at the prefix. For those entries with the same prefix, that's the only time you have to compare the magnitudes. If you're tracking, your sequence should have looked something like this. 2.84 terazoinks is the largest entry, followed by 8.7 gigazoinks, 23.8 megazoinks, 33 kilozoinks, 24 zoinks, 196 millizoinks, 47 millizoinks, 47 microzoinks, and finally the smallest entry, 22 picozoinks. There you have it. All of our original unwieldy numbers have now been placed in engineering format and arranged in a proper sequence befitting their magnitude. I'm asking you to consider 2 major advantages of engineering prefixes. 1, the numbers expressed in engineering format are far more compact and far easier to write and read than the original numbers. There's no tangled string of confusing zeros, and the coefficient, being the only part of the original number that actually delivers information, is readily apparent. 2, and this is important, magnitude is easily discernible. Ignore the coefficient. A tera is 1,000 times larger than a giga. A giga is 1,000 times larger than a mega, and so on. Only in cases of equal prefixes, as in the case of 196 millizoinks and 47 millizoinks, does one actually have to go to the trouble of comparing numbers. All right, that about wraps up this introductory discussion on engineering notation. Stay tuned for upcoming lectures featuring engineering notation on the scientific calculator and conversions between different engineering prefixes. In conclusion, this lecture took a look at engineering notation. We learned engineering prefixes make unusually large or unusually small numbers easier to read, write, and most importantly, conceptualize. Additionally, we learned engineering prefixes can be used to quickly ascertain whether a number is greater, much greater, smaller, or much smaller than another. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.